Well, welcome back. We're now doing section 7.2 pre-section videos and getting an idea of what more we can do with this integral stuff. And the next thing we're doing is something called volume rotation. This is the first method. There are two methods. This is the first method in 7.2 called the disk washer method, or vertical slicing method, as you want to call it that. The volume of rotation. The idea is you are taking a particular function, we'll call him f of x, and we're going to be rotating it around the x-axis. So, and as we rotate it around the x-axis, or whatever other axis we can come up with, when we rotate it, we're going to create this circular volume. And the way I describe it to my students is this. We are looking at trying to do things like wood lathe work. You know, when you got a piece of wood on a wood lathe and it spins and you take a chisel and you chisel out this thing, you make a perfectly circular figure out of this thing as this thing has been chiseled out. And what we're trying to do here is figure out how much volume is in this three-dimensional shape that you created by taking this line and rotating them around the x-axis. Now, when you're rotating it, you make circles. And you know the area of a circle is pi r squared. And your radius is actually the function here. So the radius ends up being the function. So the area ends up being pi times f of x, the function, squared. But then it's got a little bit of a width there, times the width of it, which is delta x on that little slither. We're going to do what we call slicing method. And then what you're going to do is you can make an infinite number of slices in this. To get volume, you sum up the slices. So it creates this formula for volume. When you get the areas and you sum up the areas, you end up making that volume. So the volume, as you turn this into calculus, becomes pi. The summation turns into the integral of your function squared, and the delta x turns into dx from a to b, and it creates what we call the disk method formula. So it's really based upon the area of a circle, making a vertical slice in it, and then summing up an infinite number of slices that you could have made, and creates an integral form from the summation. So, and your professors will get into that a little deeper and how these things were derived. But so your formula is volume is equal to pi times integral of the function squared dx from a to b. So it's slightly different from the area formulas. There you have an integral of the function from a to b, but you're squaring the function and sticking a pi from the formula for the area of a circle, dx. Now we have this, what we call the disk method, because it's solid. And then what happens if we have this region and we have an outside and inside, or a top-bottom part of this guy? Well, we create what we call a washer when you rotate this part around, if you have an outside-inside, because that means there's a part inside that you're removing, and creates the washer method. And the washer method is very similar. It's volume equals pi times integral of the function squared minus g of x squared, which is basically the top squared minus the bottom squared of a region. Again, this idea is coming from the area between two curves. And so if I have a top bottom or an outer inner, as you're looking at the outside and inside as it's being rotated around a particular axis, we have this particular formula called the washer formula. And this one's doing the horizontal slicing because, okay. So, as we look at this thing, we have, like I said, we can do top and bottom dx. But if we want to decide we want to rotate it around a particular y-axis going this way, but the functions have to be in the same axis as the region due to the disk washer method. So if I have functions in terms of y, dy, this would be more like the right squared minus the left squared. But that would be dy, which means I have to have function in terms of y, and these would have to be y bounds. So we're using some of those same similar formulas that we had between area between two curves, except we're applying this formula from circles to square the functions and throwing a pi on it to give me volume rotation. So let's take a look here. All right, the first question is this. Sketch and find the volume of the region in the first quadrant bounded by the curves y equals x cubed, y equals 0, and x equals 3. rotate it around the x-axis. All right. So the first thing I want to do is, again, just like with area, I need to draw these regions. It's very visual. We all played around with x cubed graph. You know that one by heart. X cubed is the squiggle graph. It goes to the first and third quadrant. So there it is, y equals x cubed. Here's my y-axis, here's my x-axis. I have the line y equals 0. Y equals 0 is also known as the x-axis. And then I got the line x equals 3. So 1, 2, 3, right about there. So that's a vertical line, cutting right through there. Here's the line x equals 3. And there's the region that we want to rotate. And we want to rotate this around the x-axis. My functions are in terms of x, and I'm rotating around the x-axis. So this will be the classic disc washer method, and I put those two methods together, but this one honestly would be more of a disc because it would be solid. If I rotate this thing around the x-axis, it's going to be a solid piece. We're not removing anything out of it. So the formula for the disc is volume equals pi times integral from a to b of f of x squared that way dx. So, and that would be the top, because eventually you really do have a bottom here, but y equals 0, so that part doesn't show up. So my function is x cubed, so this becomes volume equals pi times integral of x cubed, but for volume rotation you have to square your function dx from 0 to 3 is my bounds. Of course, John's fundamental theorem of calculus always applies here. Clean up your algebra first. If I'm trying to integrate the integral pi times integral from 0 to 3 of x cubed squared, how do I deal with an x cubed squared here? Would be, I would have to clean it up. Power to a power I multiply, so that would be x to the 6th power dx. And then I would integrate, so this will be pi times, pi is a constant, leaves out front, integral x to the 6 is x to the 7 over 7, evaluated from 0 to 3. And then I plug in top minus plug in bottom fundamental theorem of calculus. That'll be 3 to the 7th over 7 minus pi times 0 to the 7th over 7. Now that's 0, so that goes away. So 3 to the 7th, it's nothing but a number on the calculator there. That's, of course I made this up, 2,187 over 7, and don't forget your pi on it. But this time it would be units cubed, because you found the volume in rotating this region. And just to give yourself kind of a visual perspective of what you're doing here is, and I always draw this on a different graph, but there's my region right here. And I've rotated around the x-axis, so I've got this reverse image down here. Come down and you rotated him, so you've got this bell-looking thing, but it's nice and solid throughout, and you found the volume of this, and you've got to think 3D on this stuff, or what this stuff starts to look like. Now, when it comes to these kind of problems on web work, on tests, and the like, they're going to ask you for two different things. Setting up the integral that defines the volume, and actually evaluating the integral. So a lot of these problems, they have two different parts. This is the integral form that sets up the integral to calculate the volume, and this is after you calculate it, this is the actual volume that you get. Next problem. Sketch and find the volume of the region bounded by the curves y equals x cubed, there it is again, but y equals 8, x equals 0 around the x-axis. Again, the reason why we put this one in here is to emphasize the idea of pay attention to where the region is located at. So once again, we do our freehand drawing. You can use a graphing calculator if you're allowed to have that on this particular part of the class. So y equals x cubed, that's again a basic function, so you actually don't need a calculator for this. It's my squiggly line. Here's y equals x cubed. Y equals 8. Now that's a line up here, so I'm going to draw him horizontal line here. Y equals 8. X equals 0. X equals 0 is the also known as the y-axis. There's x equals 0. So the region has been captured by this, and this is important to see. Because I got this region, I got this region, I got this region, so it's got to be stuff in there. Okay. And again, we want to rotate this around the x-axis. But this time, look at what they told me to do. Just set up the integral. You'll see a lot of these pre-section quizzes that you have to use. You're going to set up the integral, and a lot of the test, I guarantee you, is not about also integrating this stuff. It's about setting up the integral. That's our focus in terms of applications of these integrals. Can you set up an integral that's going to evaluate this thing? But now here comes the deal. You've got to visualize this thing being rotated. We're going around the x-axis. So around the x-axis, there is a top function and a bottom function that we're trying to find this thing. So we're actually going to be rotating this thing out, and there's a part being removed. So this would be what we call the washer formula, which is volume would be pi times integral of what I call f of x squared minus g of x squared, the top minus bottom, or the outside minus the inside, the inner that you're removing, dx, because again we're rotating around the x-axis. My functions in terms of x from a to b. So plugging it in, this would be volume equals pi times integral of the top function, which is y equals 8 squared, minus the bottom function, which is y equals x cubed squared, dx, and my bounds are my numbers. Now, this one is x equals 0, but where does this stuff meet up at? Well, that's where the intersection of y equals x cubed meets up with 8. So I would end up having to take the cube root of both sides. So x is equal to, the cube root of 8 is 2. So this is the next point, 2. That goes from 0 to 2. So, and they wanted me to, quote, just set up the integral using this one because of the way it's structured, is the shell method. So this is the integral, which is pi times integral from 0 to 2 of 8 squared minus x cubed squared dx. And what you would, if you evaluate this, you would square 8 to 64. Power to a power you multiply, so that'll be x to the 6th, integrate, 64x minus x to the 7th over 7, plug in top, plug in bottom, and crunch yourself out a number. And what that would find would be, now you got to begin visualizing this bowl shape coming up here, and you've got this region, and you're rotating around the x-axis. You get this reverse image down here, and then you got this rotation. So on this side it's solid, but this part has been kind of scooped out as you've got this circular part. So this is what you found the volume of. Very visual stuff. So hopefully you have good skills at drawing pictures. Okay. Another one is this problem here, and I tried to, basically get these things to be a little more user-friendly in terms of writing up these notes and stuff. But the washer method boils down to this, because occasionally they'll want you to rotate around something other than just a plain old x-axis here, or possibly the y-axis, and that is this. So, in general form, the shell method turns into volume is the is pi times integral of what we call the big functional radius squared minus the little functional radius squared dx. And you use this. The big functional radius, what I call big radius, and that's the capital letters there, is the distance between the axis of rotation and the outside big radius. And the little functional radius little here, is the distance between the axis of rotation and the inside. So let me show you an example of using this particular formula. Okay. Sketch and find the region of in the first quadrant of the curves bounded by y equals x cubed, y equals 0, x equals 3, rotated about the line y equals -1. So here we go. First thing you've got to do is you've got to get that visual perspective of the region you're going to rotate. Again, it's classic y equals x cubed, so it's a little squiggly line there. So there's the line y equals x cubed. Y equals 0. Y equals 0 is also known as the x-axis. So y equals 0 is the x-axis there. And then I got x equals 3. So somewhere over here, declare it to be 3. That's a vertical line. X equals 3. Again, this would be the area that we are rotating here. But now, look here. They want me to rotate about the line y equals -1. Y equals -1 is down below here. There's -1 on the y-axis. Y equals is a horizontal line. y equals -1, and this is the axis. It's no longer the x-axis or the y-axis or anything like that. So now, the formula for calculating volume is this pi times integral from a to b of my big functional radius squared minus my little functional radius squared dx. Reason why the dx is because y equals -1 is parallel to the x-axis, and that means we're rotating it parallel to the x-axis way, which is vertical method, slicing into the parallel to the x-axis. So that's why the dx. Parallel to the x-axis, use dx. If I was rotating it this way using the disc washer method, it would be dy. Now, I need to calculate what my big radius is. Big radius, as we defined it to be up here, this big functional radius is the distance between the axis of rotation and the outside function, which creates our big radius. So here's my axis of rotation. The outside, here's the region. The outside of that region is on the top side. And anytime you're doing distance, it's either top minus bottom or right minus left. Those words are going to come back and haunt you. Top minus bottom or right minus left when I'm looking for distances. So my big radius would be the top, which is the x cubed, minus the bottom, which is the actual axis, -1. So it's top minus bottom to actually get the distance that you're covering for the big radius. Now, of course, you'll clean this up. Minus a -1, my big radius function is going to be x cubed plus 1. And now my little functional radius would be, again, from the axis of rotation to the inside part of my region. Again, it's top minus bottom to calculate my distance here because I'm going vertically. So top is y equals 0. Minus bottom is, again, minus -1. So when I clean this up, I get r equals, a minus is a plus, so r equals 1, little radius. So my volume would be pi times integral of the big functional radius, which is x cubed plus 1 squared, minus my little functional radius, which is 1 squared dx. And now a and b are my bounds on my points of intersection here, one of my region, which is one is clearly x equals 3 is one point, and the other one is the origin right here. They meet up, x cubed and the y equals 0. So I could set them equal to each other and solve, but it's pretty easy. It's x equals 0 there. So it's from 0 to 3. And again, in this problem, they just say just set up the integral. So this would be my solution. You got to get this idea of you don't just rotate around the x-axis, you could rotate around other axes. So y equals -1 axis just gives you that you have to start calculating radius distance as this thing's being rotated. And just to give you a visual perspective of what you're calculating the volume of, you've got this region, which is up here. There was the x cubed thing up here, and then coming back down. And there's the region. This is my axis of rotation. So you get this, as you rotate this region, this reverse image down below the y equals -1 axis. Looks like this. I'm trying to sketch it in lightly for you there. And then as you rotate this particular part, it's like a shadow, you got this part and this part, and this. You get this kind of spool looking thing that you're creating. That's what this will calculate in units cubed. And one more problem on this particular section on the pre-section quiz here. Pre-section video to set you up for the quiz. Sketch and find the volume. This time we're going to make you find it. Okay. Sketch and find the volume of the region in the first quadrant bounded by the curves y equals x cubed and y equals x. Again, rotate around the x-axis. Okay. So I'm going to draw my region here. Here's my y equals x cubed. Y equals x. There's a 45-degree line here. Here comes a line y equals x. In the first quadrant, so we're clearly talking about this particular region here. Here's your y-axis. Here's your x-axis. But before I find anything, I need to find the points of intersection of my region. One's pretty obvious, it's 0, but the other one, I'm going to have to take my two equations, x cubed and y equals x, and set them equal to each other to find points of intersection. It's a cubic, so it's a polynomial. I'll set it equal to 0, so I'm going to subtract x from both sides. So I get x cubed minus x equals 0. I can factor out an x, leaving me with x squared minus 1 equals 0. That factors into difference of squares, x plus 1 times x minus 1 equals 0. Set each factor equal to 0 and solve. Oops, x plus 1, x minus 1. Get it back there. Okay, minus 1 equals 0. And then you solve, you get x equals negative 1, x equals 1, and x equals 0. So there's a negative 1, a positive 1, and 0, but we only wanted the first quadrant here, bounded by the first quadrant, so you don't care about this dude. It's 0 and 1 are my points of intersection. But we want to rotate around the x-axis. When rotating around the x-axis, you've got your big functional radius from the axis of rotation to the outside edge. But when you're going around the x-axis, you're going to use this formula. Volume equals pi times integral of the f of x, which is your top function, squared, minus g of x, which is your bottom function, squared dx from a to b. This is your big radius, this is your little radius, but when the y equals 0 or the x-axis, subtracting 0 just gives you the functionals back. That's the connection between the two. So volume equals pi times integral from a to b. The top part of my function is the straight line part, which is y equals x, and you have to square it according to the formula, minus the bottom, there's my bottom right there, which is x cubed squared dx. So this is my formula. So if they wanted me to set up the integral, here it is right there, but they wanted me to evaluate this as well. So set it up first. There's my answer for setting up. Then clean them up and then integrate. So volume equals pi times integral. Oh, forgot my bounds. My bounds would be from 0 to 1 of x squared minus, so this would be 0 to 1 there. Power to a power of multiply minus x to the 6th dx. So volume equals pi times integral of x squared is x cubed over 3 minus integral of x to the 6th is x to the 7th over 7. Evaluated from 0 to 1. Applying a little fundamental thermocalculus here, that'll be pi times 0 cubed over 3, plug in 1 first, plug in top, 1 cubed over 3 minus 1 to the 7th over 7, minus pi times plug in bottom, which is 0 cubed over 3 minus 0 to the 7th over 7. But who am I kidding myself? That's just 0. We love plugging in zeros into most things. So when I clean this up, so volume is equal to pi times 1 cubed is 1 third minus 1 to the 7th is 1 7th minus 0. And cleaning up my old fractions there. 1 third minus 1 7th. I can go for the common denominator thing, or I can just use my calculator, which is what I'm doing. I end up getting 4 pi over 21. Don't forget your pi, because this is that rotation stuff here. 4 pi over 21 units cubed. This will be my volume. And for those engineer types out there, 4 pi divided by 21, I really am using my calculator here, would give me, this would be the x volume, 0.5983906,007 units cubed. But for a lot of the problems, they're going to leave the pi in the answer as a fraction. And what did you just find? All right, you found taking this region, rotating around the x-axis. So to get a little visual of that, we've got this region right here, rotating around, so you get that reverse image around the x-axis. And so you take this and rotate it, so it's kind of solid flat on the outside, but you scooped out quite a bit of the inside. So this is what you calculated the volume of. Hope this has been helpful, and I know your professor is going to go into great detail on taking these problems and rotating around the x-axis, the y-axis, and then other axes like y equals -1 and stuff. So there's the forms and then the forms that have been converted over. So pay a very close attention to this, but it's actually a very unique and important section, and gets into things like wood lathe and metalwork and stuff like that. You get some real world applications of stuff. Well, I hope this has been helpful, and I'll see you on the next video.